So what should a theory, we were talking about the Bohr theory, what should a theory do? Be able to predict and also give a fundamental description. So what is the fundamental description of atoms, or what's happening with electrons in atoms?
We have the protons and the nucleus.
Yeah, the electrons are orbiting around the nucleus, correct? So that's the fundamental description. And one of the predictions that Bohr theory was able to do was to predict the ionization energy. And so if we look at the ionization energy is taking the electron from the first orbit, where it normally is. This first orbit's the lowest energy possible for the electron. Could it go any lower than this? No. And then promoting it up to the infinite orbit. We call this an n1 to n infinity, where n is the number, n equals 1. I should say that n equals infinity. That's another way of saying this. Transition. So we could go ahead and predict the energy here. The energy for the 1 to infinity is going to equal delta E, where E final is E infinity, E initial is E1. And so that E infinity is just going to be minus R sub H over infinity squared, minus E1 is just minus R sub H over 1 squared. And so looking at this, this one's going to approach 0. This one is just going to equal plus 2.179 times 10 to the minus, what was it, 19 joules? 18 joules? Minus 18 joules. I recall. Was that the Rydberg, RH? What do you have in your notes? 10 to the minus 18. Is that very much energy?
No.
No, but we have to change our perspective, right? When we're dealing with this type of quantum, we have to think in two different energy universes. One at the macroscopic level. At the macroscopic level, which we've been dealing with in Chapter 7, is this very much energy? Could you warm up a cup of coffee with this? No, this is just nothing. This is 0, right? Negligible. But at the microscopic, at the very, very small level, when we're talking about a single atom, this is quite a bit of energy. And to bring it into the macroscopic scale, what we typically do is we change the units. This is joules per atom. What we can do is we can times this by Avogadro's number to get joules or kilojoules per mole. So let's go ahead and do that. Multiply this number by Avogadro's number, and let's see what we get.
What does it say under the negative R8?
This one?
Yeah.
Here?
Yeah.
1 squared. It says n squared, so n is equal to 1, and then we square it. So does somebody have it? What is it? 131? 2193.
There's a 1.1 to 131.
Oh, 131, 2193. Okay, 131, 2193. All right, probably in joules per mole, this isn't so convenient. And so let's go ahead and move the decimal place 1, 2, 3 over, and we'll get 1,312.1 kilojoules per mole. And so this this is maybe one of the, I guess you could say it's a success story for the Bohr theory. You know, it could predict the ionization energy. And this would be the ionization energy kilojoules per mole for hydrogen. But we try to apply it to other things, and then what happens? It doesn't work. Okay. And so this checks. And so the problem is Bohr theory can predict energies for one electron species only. And so what they did was they modified this because they're trying to predict energies for other species. And the modification is this. It turns out E sub n is equal to z squared minus z squared r sub h over n squared. And so if they, where z is the atomic number. Z, what do you recall about z? Z is the number of what? Number of protons. So the more protons we have there, that's going to influence the energy of the electron. But it only works for one electron. It could predict the spectra. And so from this, we can predict spectra, etc. I'll just say spectral lines. You know, the lines in the spectrum that we see. But if you try to apply this to helium, for helium it fails. For helium, etc., fails. And therefore, if the theory conflicts with experiment, then who's going to win? Experiment.
What do you mean by etc.?
Helium, everything else in the periodic table.
It's because we have more than one electron.
Yes. For helium and everything else with more than one electron.
So is it only the Bohr fails, or with the Z, the negative Z?
Well, no matter how you change this Rydberg equation to modify it for helium, it doesn't work. And so it fails. They couldn't make any changes to make this work. And so what happened was this. Two developments after this led to modern quantum mechanics. And so two, let's say, developments led to our modern day theory. And our modern day theory is quantum mechanics.
What are those two developments? What are those two?
Yeah, so let's talk about the two developments that led to this. And so the first development was this. The particle wave duality of matter. Let's say all matter. And so this was de Broglie. What he said that all matter behaves like waves. And so he came up with an equation lambda for matter. Lambda for matter is equal to this. Planck's constant divided by the mass times the velocity. All right, this is not for light, you know, lambda for light is equal to hc, sorry, not hc. We'll do it the first way. C over nu, which is not equal to hc over the E. Energy. This is for light. This is for matter. And so, particle wave duality of matter. There is particle wave duality for light. And so that was already known during Bohr's time. No. There's particle wave duality for light. We know that light consists of electromagnetic radiation, which occurs as the oscillating waves, electric field, magnetic field. And so normally when we think about light, we think of waves, right? But we can also think in terms of particles, because if we think in terms of particles, a particle of gamma radiation versus a particle of red radiation, particle of gamma radiation is going to pack more punch, can cause more damage. We call these particles the photons. And so a gamma ray photon is much more energetic than a red light photon. But these photons, they don't have any mass, rest mass to them. And so in a way, it's not real a particle in the sense that we think of objects. All right. Then the second development was the Heisenberg uncertainty principle. The Heisenberg uncertainty principle says this. It just says that, well, there are different readings on this. One thing that it says is you can't make predictions at these very small levels, accurate predictions. Small levels being at the level of the electron. And so, summing it up, it just says simply, you cannot pinpoint simultaneously, I should say, the position and energy of the electron. You can pinpoint the position of the electron, but then you're not sure about its energy, or you can pinpoint the energy, but you're not sure exactly what the position is. You can't know both simultaneously with good precision.
With both uses momentum.
Yeah. Momentum is energy. Also.
Is it velocity also?
Momentum. Mass times velocity. Momentum is mass times velocity. That's our momentum. But momentum, we aren't going to be, yes, technically it is momentum. In the Heisenberg has an equation. In the Heisenberg equation, there's a fundamental limit to your precision. And in the Heisenberg equation, you don't have to memorize it, but the uncertainty in x, the position we call delta x, times the uncertainty in the momentum. Momentum, what symbol did they use? M? For momentum? It has to be greater than Yeah, something like h over 4 pi, right? Where h is the, this is a fundamental limit. But you know, these uncertainties are actually very small, but the electron's very small. It's like your energy. Remember when you're thinking about your energy, you know, 10 to the minus 18 joules, what's that going to do to a cup of coffee? Nothing, right? And so normally if we think about 10 to the minus 18 joules, that you ignore that. You don't even care because that's nothing. That's like zero, right? But when you're on the scale of an electron, 10 to the minus 18 joules is enough to kick you from, you know, in the Bohr model, it's enough to kick you from the first orbit all the way to the infinite orbit, infinitely far away. So if you're a single electron, that's a huge amount of energy, right? When we're dealing with these uncertainties, you know, it depends on the scale. When we're dealing with macroscopic, you know, how big is this? When we're dealing with macroscopic objects, the amount of uncertainty in the precision, what do you think? The amount of uncertainty with macroscopic objects like a car or a rocket ship or something like that, you know, is
Very small.
very small. In fact, it's so small, it's kind of negligible. Pretty much this is negligible. But when we're dealing with, you know, like an electron, then it becomes significant. And so do you see there's two kinds, we have to shift our mind from one universe to the other. The macroscopic universe to the microscopic, for lack of, microscopic is what people usually call it, but you can't see it with a microscope. I mean, it's way smaller than anything you can see with a microscope, right? And so the uncertainty becomes quite significant when you're dealing with a electron, right? This is why, I mean, this is a fundamental part of all matter, you know, this Heisenberg uncertainty principle, but, you know, people didn't notice it until they started dealing with electrons, right? Because, like, for example, did they have to worry about the Heisenberg uncertainty principle when they're doing a moon flight, let's say? You know, Saturn rocket goes to the moon. Are they gonna? Oh, maybe I'm gonna miss the moon, you know, because I got uncertainty in position and momentum, right? Is that uncertainty I'm gonna miss the moon? No, I mean the uncertainty is so small. And so this is why in physics they didn't notice these things until they started dealing with the hydrogen atom. And when they started dealing with the hydrogen atom, that's when, wow, became. And the same thing with matter. You know, matter waves, when we're thinking about macroscopic objects, these matter waves are insignificant. You know, these matter waves, you know, are yeah, but when we start dealing with an electron, then the matter waves become significant. So maybe let's talk about the matter waves first here. So let me talk about waves just briefly. If I look at it like a guitar string here, or a musical string, and you pluck it, right? If you pluck this string, then are all energies allowed? In other words, are all frequencies of sound allowed for that string? That is, you can get any sound you want from the string because all frequencies of sound are allowed. No. Because this is what we call a standing wave here, and you'll know, like, this is when you look at a guitar or a piano or something like that. There's a whole bunch of strings, right? Different thicknesses. They're going to have different frequencies. Well, the same thing here. You know, this is allowed if you pluck it, and we get what we call 1/2 lambda. Here, so 1/2 lambda is allowed. But let's say I want 1/4 lambda. I don't like that sound. I want 1/4 lambda out of that string. Am I going to be able to get 1/4 lambda out of this string? No, that would be like this. That would be forbidden. 1/4 lambda is forbidden. Okay, now if I try to get another frequency out of this, another wavelength, what would it be? Next one. The next one I can get would be next one I can get. Well, this would be higher energy. Would be if I were to get one full lambda in there. So here, the next one allowed is this. This would be 2 1/2 lambdas. In other words, a full lambda, full wavelength. Right? What would the next one be allowed? Can I get 2.5? Well, let's see. Yeah, I can get 1.5 wavelengths in there. So if I do that, it'll be here. Let's get that, and I'll get this drawing. It's not terribly great, but peeked out here. Can you see? In other words, I could get 3 1/2 lambdas in there. 3 1/2 lambdas. And then, you know what I'm going to see? I'm going to see that the energies of the guitar string are quantized. They're quantized in the equation for these. These are the allowed. The allowed are n times 1/2 lambda, where n is equal to 1, 2, ... Right? Now, if we see this, you know, this is going to be kind of a big jump from this energy to this energy, right? You're going to have to get more energy transfer from your finger to the string here, right, to pluck it this hard or this hard, correct? It's going to be big jumps. Okay, this is where the wavelength and the object are, you know, comparable in size. Lambda and the object are comparable in size. All these pens are, oh, I found them. Lambda and object comparable in size, in dimension. But when the lambda is much smaller than the object, but when lambda is much smaller than the object, we see something like this. All right, if we continue this up, eventually, you know, is 1 million half wavelengths allowed? Yeah, 1 million half wavelengths are allowed, so what would that look like? Something, I can't even do it that small, but let's imagine this. Let's imagine there are 1 million 1/2 lambdas. That's allowed, right? What's the next energy that's allowed? 1 million and 1. And so the next allowed energy is 1 million and 1. Actually, let me draw a little bit higher. 1 million and 1. And so I just got to squeeze one more half lambda in here, right? And so this would be 1 million and 1 1/2 lambdas. Now here, you see the wavelength is very small compared to the object, right? And the delta E here, what do you think about the energy difference between these two? You know, how big is the gap? Because I'll tell you, when I'm plucking it hard here, I got to pluck it a lot harder to get this, right? Because the energy gap here is kind of big. This is kind of big, the energy gap. But when I look over here, Is the energy gap going to be, I'm going to really have to plug it a lot harder to get that extra 1? No. In fact, the difference in energy between having 1 million and 1 million and 1 would be like negligible, extremely small. Delta E is kind of, I'm just going to write negligible because it's such a tiny, negligible. I mean, I should go to extreme. Let's go, I'm going to go 1 trillion. What's the next one allowed? 1 trillion and 1. Much energy difference? No. And so, well, it's the same thing here. And so what's the next one allowed after this? 1 million and 2. 1 million and 3. And so what happens is when the wavelength is very small compared to the object, the energies are so tightly packed together, they're like continuous. And so this, how do we apply this to what we're looking at? Well, let's apply it like this. We'll do an example here. Remember the tungsten light bulb? The incandescent light bulb. The tungsten light bulb. The tungsten light bulb had a big piece of metal here. And the tungsten filament, let's say. This tungsten solid. How big is an electron? Very small. And so when we excite the electron, I mean, here, let's say the electron is like this. And then I say, okay, I'm going to try to excite this with some red light. If I excite this electron with red light, it just pops up a little higher. And so here I just add another half wavelength in there. In other words, an electron in tungsten metal is like this scenario, where the wavelength is small compared to the object. And so the matter wavelength is small compared to object. And so here, if the wavelength is small compared to the object, then the jump up here is going to be very small. Let's say there are trillion half wavelengths, it would be 1,000,000,001 the next. How much energy does it cost to promote an electron from 1 trillion to 1,000,000,001? Negligible. I mean, very tiny amount of energy, right? And so basically I can keep exciting the electron, exciting it more, and then what I see is I see a continuum of allowed energies. This is why I got white light from here, because I can excite it to different levels. Excite the electron to, and just add more. Versus this. Now, if I took that tungsten, right? If I took that tungsten and made a tungsten atom, and I try to do the same thing. Now, let's say I have a tungsten atom here. Here's the nucleus, the tungsten atom. And I got this electron out here. Now, the electron is confined around the nucleus. And so it's like the electron is kind of like the guitar string as well. And so it turns out that the electron is moving at some wavelength, let's say, like this. This isn't such a great drawing, but it's like the guitar string because of the waves work. Now, if I look at this, I could fit, let's say this is 4 half wavelengths in here. But let's try to go to 4.3 half wavelengths. if I try to go to 4.3 and squeeze in a little bit more here, if I try to squeeze in a little bit more here, then eventually what happens is this. And eventually what happens is I have a peak of a wave coincide with a valley of a wave. And when a peak of a wave and a valley coincide, the waves cancel each other out. And so we call this destructive interference. And so if the half wavelengths are slightly off, we get destructive interference. This is what would happen to a guitar string if you try to put a quarter wave in there. It's just not going to happen in that sense. And so here we have a destructive interference where the waves cancel. And this is forbidden. This would be a forbidden energy. Let's see if I can get this one. And so what's the next allowed? Well, the next allowed would be squeezing another half wavelength in here. If I squeeze another half wavelength, then that's allowed. And so the situation is there's going to be a kind of a jump, right? Because the wavelength is comparable to the size of the object. The object in this case is the atom. And if the wavelength is comparable to the size of the atom, then we've got to fit the right number of half wavelengths in there. There's an analogy here. You know, the analogy is this. The analogy is an electron in a box. You know, the electron's kind of confined in a box here. And if an electron is confined in a box, then not any wavelength is allowed. And so, for example, we could have 1/2 wavelength here, or we could have 2/2 wavelengths here, or a full wave. Or we could have 3/2 wavelengths, right? This is just like the guitar string. Otherwise, we get destructive interference because the electron's confined in this box. Well, the same thing here. The electron is confined in the atom, which is the box. Now, if the half wavelengths are so small, then what happens? Well, this is what's going to happen. We see the energy levels here. We'll just plot it up here. Okay, so we got a half wavelength in there. We got 2 half wavelengths in there. And then 3. And what happens is the energy gaps start to get smaller and smaller. And eventually they're so tight because, you know, think about it, from 0 joules down to minus 2.179, this is for the hydrogen atom, times 10 to the minus 18. 0 joules is the highest energy we can have, right, for the H atom. And we have to fit an infinite, you know, because this goes to n equals infinity. And so basically I have to draw an infinite set of lines from minus 2.179 times 10 to the minus 18 to 0 joules. And so pretty soon those energy levels have to get so tight that it appears to be a continuum. And so we see these big gaps down here for sure, but when we get to the higher energy levels, just like that. So what is the wavelength of an electron? Well, let's take a look. And we can do two quick de Broglie calculations. One, does somebody have their book? All right, the first one is, let's calculate the lambda for an electron that's moving at 1/10 the speed of light. And so this is going to equal HMV. H, I know, 6.626 times 10 to the minus 34 joules times seconds. Mass. The mass of the electron, does somebody have that memorized, or does somebody have in kilograms or grams? We want it in kilograms, actually. The mass of an electron in kilograms. 9.11 times 10 to the negative 31 kilograms. Thanks. Physics people. And then V, the velocity is going to be 0.1 the speed of light. And so this is 0.1 times the speed of light, 3.00 times 10 to the 8 meters per second. We're just going to assume it's moving that fast.
Well, let's say right next to the first lambda electron.
Equals
The top one.
H,
No, the top.
assume.
Right, okay.
Assume the velocity is 0.1. So here we're going to have to change the joules. Let's change that into kilograms, meters squared per second squared. And so let's see, the seconds will cancel, kilograms cancel, one of the meters cancel, and that leaves us with the wavelength of meters. We could use dimensional analysis to tell us, did we get the right equation? Sometimes it's easy to forget the equations. But using dimensional analysis can definitely tell you if you wrote it wrong, you know, if the units don't work out. Ah. Okay. 2.426 times 10 to the negative 11 meters. This is equal to 24.26 times 10 to the minus 10 meters, which is equal to 242.6 times 10 to the did I get that right?
No, it's kilometer, not meter.
Kilometers?
Yeah.
Okay.
Why would it be kilometers?
Should be in meters. Unless you, did you convert it to kilometers?
Let me check.
Actually, I went the wrong way. It should be 0.2. If this goes smaller, wait, if this goes smaller, this has to go bigger? Yeah. Is that right? No. No, that's not right. 0.242? That's right? Okay, and if this goes bigger, 24.2 times 10 to the minus 12. Okay, so this would be meters, 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 correct?
Would be 10 to the minus 14 meter.
10 to the minus 14 meters? Is that what you guys got? This one, 2.42 times 10 to the minus 14. 10 to the minus 11. 10 to the minus 11 is correct. Yeah, 10 to the minus 11 is correct. But I changed it to this. Do you know why I changed it to this? Have you ever heard of 10 to the minus 10 meters? Yeah, 10 to the minus 10 meters is given a special name. It's called an angstrom. And do you know why it's given a special name?
Commonly used.
Why is angstrom given a special name? Angstrom is given a special name because that's about the size of an atom. Atoms have radii from 1 angstrom to 5, 6 angstroms. And so if I look at it, this is a quarter angstrom, which means that the wavelength is about the size, you know, 1/4 the size of a kind of an atom. Half angstrom, so it is half angstrom. And so anyway, or this 10 to the minus 12 meters is called a picometer. And the significance of a picometer is that atoms are about 100 to hundreds of picometers in size. And so if we look at the wavelength, is the wavelength significant compared to the size of the object? In this case, the atom? Yes. You know, if this electron were confined in a big piece of metal like tungsten, even though, like, let's say I had a 10 centimeter filament or a 5 centimeter filament of tungsten metal, you know, if I had 5 centimeters, is this wavelength significant? No, this wavelength is totally insignificant. But if I go down to a tungsten atom, which is hundreds of picometers in size, then is the wavelength significant? Yes. And so this is what gives the odd behavior. For example, tungsten metal, a bar of it, behaves like a black body. Whereas a tungsten atom, if I tried to make a lamp out of using tungsten atoms vaporized off the metal, would that work? No, it would give me a line spectrum where there are distinct big jumps in energy, you know, corresponding to the next allowed energy there. You know, these wavelengths are very small, and in fact, what happens as the object becomes more massive? As the object becomes more massive, the wavelength gets even smaller. And so we could just do a quick calculation of a baseball. Let's do lambda. You know, about how much does a baseball weigh? Does somebody know? A kilogram, or well, it's gotta be less than a kilogram. Let's say 500 grams. Okay. Ask Siri. You're right. I should ask Siri.
145 grams.
125 grams? 145 grams? Thanks, yeah. 145 grams. Let's say this velocity. What velocity should we pick? 100 kilometers an hour? How fast? 70 kilometers an hour?
But arm pitches like 80 miles an hour.
80 miles an hour, so
that's like over 100.
over 100. Let's say 140. 140, I think, is around 80. Is that right? Let's go 140 kilometers an hour, which is how many meters per second? So let's figure that out. So 1,000 meters per kilometer and 60 minutes per hour, 60 seconds per minute. What does it come out to?
38.89.
38.89 meters per second. All right, this will be a velocity, and we have to do this in kilograms, 0.145 kilograms of the mass.
Wait, what? 30?
Hmm?
No, that can't be right.
Hours.
We have minutes.
Hours.
Over hours.
Oops, yeah, divided, sorry. Minutes, 60 minutes per hour. And for every minute, we have 60 seconds, sorry. What does it come out to? 38.89 meters per second. So let's go ahead and do this. Lambda for the baseball will equal h over mv, which comes out to
1.175 and 10⁻34.
All right, 10 to the minus 34 meters. Which for light, 10 to the minus 34 meters would be insane amount of energy. But for matter, this is not light we're dealing with, electromagnetic radiation. This is a baseball. And so let's say if somebody threw the baseball here, let's say this is 10 meters here. You know, a wavelength like this, can you fit another half wavelength easily? You know, we got 10 meters, we're throwing the baseball. What's the next allowed? The next allowed to make it to this spot would be just one more half wavelength. I don't know how many half wavelengths would be in 10 meters. Think about it. How many half wavelengths are there in 10 meters? Well, if a full wavelength is this, then a half wavelength would just be half of this, about 0.6 times 10 to the minus 34. 10 to the minus 34, the next allowed one would be just one more half wavelength above that. So it's pretty much going to be continuous in that sense. Does that make sense? In other words, the wavelength, lambda, is negligible compared to the size. The object is the playing field, let's say. You know, 10 to the minus 34, do you ever measure the field to 10 to the minus 34 meters? Could you? No, that's smaller. That's way smaller than an atom. You know? And so there, it's going to be completely irrelevant. So it turns out that that even though classical physics, you know, there's something called this. So let's say bottom line. Even though classical physics could not predict the H atom spectrum, it was used successfully to get people to the moon and back. And we can see why. Because to get people to the moon and back, that's macroscopic. And so no problem. And so even though classical physics could not predict the H atom, it was used successfully to get people to the moon and back, and continues to be used. Because these factors are negligible for that. Classical physics, though, quantum physics, underlies classical physics. If you do quantum physics and you assume macroscopic objects, then quantum physics, when you assume macroscopic objects, the equations simplify to the equations of classical physics. Equations simplify to the equations of classical physics. So what classical physics is just a simplification of quantum physics. Quantum physics is what you call the full theory, and classical physics would be a simplification of the full version of the theory. So for us though, classical physics doesn't work for us though. And so we must use the full version, quantum physics. And so for us, classical doesn't work. And there's two big contrasting things we talk about when we talk about Heisenberg. Talk about that next. In classical physics, the world is a deterministic place. That is, you could predict what's going to happen based on the present. But Heisenberg and the Heisenberg uncertainty principle means that the world is not a deterministic place. The world is a place where there are certain probabilities. And so Heisenberg uncertainty principle means that we think in terms of probability. In classical physics, we don't think in terms of probability. The world is deterministic, that is, we can't figure it out or predict. So combining these along with quantized energy into the new theory, de Broglie, Heisenberg, and previous work, say, that is quantized energy and physics involved in quantized energy. We come up with quantum. And at the heart of quantum mechanics is the Schrodinger equation. The Schrodinger equation tells us pretty much everything that we can tell about the electron. And the Schrodinger equation just says that E, actually, it's just in its simplest form, it's this H with the hat on it times psi is equal to E psi. E psi. And psi, you don't have to know how this operates. This has simpler mathematical forms where, we see what H is. But psi is the answer. But there's not just one answer, there's many answers. In fact, an infinite number of answers. But these answers are restricted. Answers to the Schrodinger equation. These answers to the Schrodinger equation we give different names to. One name we call it the wave function. Actually, all these different names mean the same thing. And so wave function, aka orbital, aka everything we can tell about the electron, everything we can say about the electron. And so contains all information about the electron. all info. All info is tricky because there's some questions, of course, you want to ask. You know, what does an electron look like? What shape is it? These kind of things, that's not an answer. It's hard because you want to know what things look like. You know, an atom looks like a ball, right? So is an electron just a mini ball, a tiny sphere? What is it? And so some things are unanswered, left unanswered, right? You know, how big is an electron? You know how big an electron is? You would think it's very small because it's very light. You know, it doesn't weigh much, right? But if they say electron, how big is it? Well, it's zero. It has no size. How can something weigh something and has zero size? You know. Because you know how big the atom is, roughly. You know, angstroms to hundreds of picometers. Or you know how big the nucleus is. It's about 10 to the minus 5 times smaller. And so electron must be a lot smaller than that, right? Anyway, electron is a very strange creature because electron, you know, when we go back to the particle wave duality, you know, in a lot of ways, electrons behave like light. In other ways, electrons actually behave like particles. And so what exactly is an electron is very difficult to answer. There's a video that I can't show it right now. Maybe I'll show it in lab. The projector doesn't work in here. Check it out. So, well, anyway, basically this is it. This wave function is going to tell us, okay, what does it tell us? It tells us this. A tells us the energy of the electron. These are energy of electrons allowed. Right. Those are the size. And so we can figure out what are the allowed electron energies. If we know the energies, then what don't we know, according to the Heisenberg uncertainty principle? The location, right? And so it tells us the energy of the electron allowed, and it tells us the probability of the position. And so let's take a look at the hydrogen atom here as an example of this. If we solve the Schrodinger equation for the hydrogen atom, actually, this clock is not working here. So how am I doing? Did I go? Oh, no, I still have time. Right, 10:55. If we solve the Schrodinger equation for the hydrogen atom, actually, I heard they make you do this in physics over here. They make you solve the Schrodinger equation for the hydrogen atom. This requires some calculus. Differential equations. It's not hard. I've done it. Calculus required. Then we're going to get answers to the Schrodinger equation. So we solve this. And do you know how many answers we get? There are, how many answers? Well, it turns out there are an infinite number of answers. Infinite number of allowed energies. Well, that's a lot. But if there are an infinite number of allowed energies, how many forbidden energies are there? Well, if there's an infinite number of allowed, that means there must be 0 forbidden energies, right? No. There are an infinite number. There are an infinite number of forbidden energies. Is that right? Could that be? No, I don't know. Somebody can correct me for that. But. So how do we know which ones are allowed and which ones are forbidden? Is there some kind of pattern to it? And it turns out, fortunately, we don't have to memorize them. Can you imagine memorizing them? That would be way too much work. There is a simple pattern. Fortunately, there is a simple pattern. It is a mathematical pattern. Simple mathematical pattern to this. It turns out that each allowed state, I use state, energy, whatever, the same, depends on 3 variables, N, L, and M. All right, so 3. These 3 variables we call 3 quantum numbers. N, L, M. And so this is the way we can figure out. It's easy to figure out all infinite if you wanted to. It's really easy to figure them out. You just have to plug it back into the equation. So we get the answer is an equation itself. And so what this means is the answer, psi NLM, is an equation itself with 3 variables. And these variables cannot be anything. In order for psi NLMs to be valid, the 3 variables must follow a set of rules. Or allowed. Everything else is forbidden. And okay, this is the rule for n. N must be 1, 2, 3, ... all the way to infinity. But it can't be anything other than those. And so these are allowed. L must be all values from 0, 1, 2, ... up to a max of n minus 1. N is called the principal quantum number or the energy level. L is called the angular momentum quantum number. So this would be principal or energy level. L would be angular momentum. momentum is related to energy as well. M is called the magnetic quantum number. And M is going to take all values from minus L plus 1 to ... 0 ... to L minus 1 to plus L. And so this ranges from minus L to plus L going in integers. And so we need to know what L is. In order to figure out M. So sometimes M is called M sub L because it depends on L, angular momentum. Okay, and all these are allowed. Everything else is forbidden. And so N tells us the energy. L tells us the shape of the probability distribution. Actually, let me just say shape of the orbital, which can be related to energy as well. There are different shapes that yield different energies depending on this. M tells us the orientation of the orbital and number. And so just say number and orientation of the orbitals. All right, so let's take a look at this quickly. Let's see what we got. So let's start off with the lowest energy. Is the 1, 0, 0. When n equals 1, if n equals 1, then the value is 0 is allowed. But an L value of 1 would be forbidden. And so, for example, here, if I did a psi 1, 1, that doesn't exist. A psi 1, 1 is forbidden. Why? Because L cannot exceed a max of n minus 1. And so this is forbidden. Okay, if L is 0, then M is 0. It goes from plus 0 to minus 0, so it's going to be 0. And so that tells us the number and the orientation. There's only one orbital of this sort. Okay, so the psi 1, 0, 0, what this is this is the lowest energy orbital. And so it tells us the energy. We aren't going to calculate the energy, but we could. The lowest energy orbital, using the calculations, we'd see the lowest energy orbital is minus 2.179 times 10 minus 18 joules from quantum mechanics, Schrödinger equation. And so this is the same number as Rydberg. And so that's good because that was experimental fact. So we calculate that, but unlike Bohr said this is the first orbit, right? In quantum mechanics, there's a different picture. In quantum mechanics, this is the way we do this. So the energy is pinpointed, which means that the position is not pinpointed. So the position is given by probability. Position given by probability because of the what principle? Heisenberg uncertainty principle. Remember Heisenberg. And so if we have the nucleus here, where's the electron? Is the electron orbiting? Bohr says it's orbiting. If it were orbiting, then that would be deterministic. We'd be able to pinpoint the electron in position. Here, we pinpointed it here, then we know it's going to be here a short time later, right? But in quantum mechanics, it's not like that. Let's say in quantum mechanics, the electron might be here in one instant, and then we want to predict 1 second later, where's that electron going to be? Can we predict that? No, all we can say is there's going to be a probability. There's going to be a probability that the electron's going to be around here. And so eventually what we'll do is we sum up all those probabilities and we get a probability map. The probability map is shown in different ways. One way is density of dots. We call it the electron cloud. And so the electron's in low energy, and that means it should be close to the nucleus. And so around close to the nucleus, we have higher probability. Farther from the nucleus, the probability drops off, like this. And so we get the dots. The density of the dots is going to tell us this. And so what we typically get is, in science we usually do a 95% confidence, right? For orbitals we do a 90%. And so we see 90% of the dots are going to be, we'll just draw a line, boundary here. So we'll call that the 90% boundary. 90% boundary is not a wall, but it just says that 90% of the dots should lie inside. That is, there's a 90% chance of finding an electron inside the boundary and a 10% chance of finding an electron outside the boundary. And so the 90% boundary helps us visualize the scale, you know, how big the orbital is. You know. But the orbital's exact size is, how big is an orbital? This is a trick question. How big is the orbital? How big is the psi 100 orbital? Well, it depends on where the probability drops to 0. And so when we do the quantum mechanics of this, then we see this. What we have to do is we take psi squared. When we square the wave function, this is equal to the probability. And so what does psi look like? When we map out psi versus the distance, this is the nucleus here. Then the wave function looks like this. It peaks at about the nucleus and then drops off here. When we look at psi squared, we'll just square that. And so we get something like this. And so this is psi squared, or the probability, and this is the nucleus. This will be the distance, r, from the nucleus. And so the further we get out from the nucleus, the lower the probability goes. But where does this intersect or converge with 0? It turns out it's going to be asymptotic to this, so it'll be at infinity. And so all orbitals are the same size, they're infinitely big, right? And so there is an exceedingly small probability that the electron's going to be way out there. There's a very, very small probability of that. But to get us a better idea of the size, that's why we have this 90% boundary, because if we look at the 90% boundary, then that's like taking 90% of the area under this curve and calling it. So this would be the 90% boundary here. Here. And that gives us better indication of this. And so sometimes what's done is that these are just represented using the 90% boundary. The 90% boundary would look like this. It'd just be a sphere around here. Here's the nucleus here. This is the 90% boundary. This is the psi 100. The psi 100 has another name. The other name for this is the 1s orbital. 1s orbital. So that's a n equals 1. When n equals 1, we only have one choice of L and M. Okay, when n equals 2, we have more choices. When n equals 2, then we can have L equals 0, right? Or L equals 1. But can we have L equals 2? No. And so we have L equals 0 or L equals 1. Let's focus with L equals 0. If L equals 0, then n equals 0. This is called the 2s orbital here. The 2s orbital is going to look like this. It's going to have an energy. The energy of this 2s orbital, actually, let's go from the Schrodinger equation here. Time. All right. What is the energy for the psi 200 orbital? It turns out the energy for this is minus r sub h over 4. That's it. And what it looks like here, so we can pinpoint the energy, and what it looks like, this orbital looks like, is this. The highest probability is going to be close to the nucleus, like this. And then we hit a point where there's 0 probability of finding the electron. This is called a node. 0 probability. And then the probability increases again out here. And then decreases down to 0. And so if we look at the 90% probability boundary, the 90% boundary would be out here, further out. Oh, this green is. Boy, that clock it's moving, but it's moving slow. I was thinking, boy, am I talking fast? So here's our 90% boundary. And so one of the things is that the 90% boundary is much bigger. This is a higher energy electron. A higher energy electron is going to have higher probability of being further from the nucleus. Well, one strange thing is this thing called a node. A node is where there's no probability. There's no chance of the electron being here. Right? And so one of the questions is, like, you know, how can we have a node? Nodes are easy to understand in terms of waves, you know. There are nodes that we've seen in waves. A node in a wave would be like this. Okay, here I have a wave, and this is a node here. And so if we think of this as being a wave, then we can visualize this as being, like, say, for example, this we call positive amplitude, and out here we call this negative amplitude. Then it seems to make sense, right? Positive amplitude, negative amplitude. And so if we think of it as a standing wave there, it makes sense. Or if we think of it in terms of a particle, how can a particle get from inside here to outside here without going through here? Is that possible? Well, let's continue this next time, so we'll stop here.